Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.
Hi, welcome to Math, the Power of Science. Today we'll be talking about particles. Particles like quarks, electrons, photons, and gluons. These particles, along with other particles, make up the universe. Some have a positive and negative charge, some have mass, and they all act like small, shrunken down balls. But they don't act like shrunken down balls. To understand this, you have to imagine that every particle has a field of quarks, electrons, gluons, photons, whatever. Usually this field has a value of 0, but in some places it has a higher value, and that's what an excitation of it is. The excitation is the particle. This means that particles aren't pinpoint objects. They're something completely different. They have a possibility of being anywhere where the excitation is. They have a higher probability of being where the excitation is high, and a lower probability of where the excitation is low. But remember, a low probability does not mean 0. It's hard to imagine particles under what we see as normal, because they aren't normal to us. They don't behave how common sense tells us they should behave. There are some properties that does fall under the normal light. They do make up everything in the universe. They do have charge, some of them, and some of them have mass. But these particles are not normal.
Quarks can and do just appear and disappear, but not out of nothing. Einstein's famous equation, E = mc squared, means that mass can turn into a lot of energy, or a lot of energy can turn into mass. In fact, the quarks that comprise a proton only make up 1% of the total mass of that proton. That's like saying I drop some quarters in a bag, and suddenly it weighs 10 pounds. There is a lot of energy in all the motion of those crazy partying particles. And there's energy in the gluon field. All of this energy contributes to the mass of the proton. E = mc squared. All we need to conserve is the total mass energy of the proton, and nothing is violated as quark-antiquark pairs pop in and out of existence. But there are a few other constraints. The total number of up quarks must be 2 more than the anti-up quarks, and there must be 1 more down quark than anti-down quarks, so that the valence quarks come to a total of 3. And the quark-antiquark pairs of other types must all cancel out, like the top quark, and the charm quark, and the strange quark, and the bottom quark. When quark pairs spontaneously appear in the proton, other properties must be conserved as well, like charge. So if a quark with charge positive 2/3 appears, its partner must have charge negative 2/3. And the spin of the particles must be opposite, and the colorlessness of the proton must be conserved. This is cool. Quarks all have color, except it's not like real color. Color in quarks is a type of charge, like the electric charge, except instead of the electromagnetic force, it corresponds to the strong force. Quarks can be red, green, and blue, like the 3 primary colors of light. And when you mix those colors, you get white light. So when I said that protons are colorless, that means that their 3 valence quarks must be red, blue, and green. So clever. The quarks can change color, but the overall color has to stay white. It turns out that the antiquark has the opposite color. So that would be like anti-red, which cancels out red. But I think the most amazing thing about quarks is that we know all of this about them without ever directly detecting one. In fact, you can never detect just one because they're never found alone. The more you separate the quarks, the more energy you have to put in to pull the quarks apart. And as you do so, you eventually put in enough energy to make up the mass of 2 new quarks that can then bind to the original 2. So next time you're told there are 3 quarks in a proton, there are 3 valence quarks and a sea of other quarks. Too many to count. Impossible to count. No, really, we can't take a snapshot. Now, if you want to find out more about quarks, check out my blog post here on 10 quirky facts about quarks. And if you want to find out how big a quark is and how we image tiny things like protons and quarks, check out my video on the smallest things in the universe. Thanks for watching.